Bismillah ar-Rahman ar-Rahim. This is lecture 3 on the static magnetic field of steady electric current. A wire carrying a current I has a magnetic field surrounding it. The magnetic field represents the force on a magnetic needle or compass. The direction of the magnetic field is taken as the direction of the north pole of the compass. As seen from the figure, the direction of the magnetic field is perpendicular to both the current, which is along Z, and the radial line, direction of rho. So B, the magnetic field, is in the direction of phi. Unlike electric field lines, the magnetic field lines are continuous lines making closed loops around the wire. The direction follows the right-hand rule. So if you hold the wire with your right hand and the thumb is pointing in the direction of the current, the fingers point in the direction of the field. The above is the essence of Ørsted's experiment on the force exerted by a current-carrying wire on a magnet. As a current-carrying conductor exerts a force on a magnet also exerts a force on a current-carrying wire. So if we take a horseshoe magnet and insert a wire carrying current I between the poles, the force on the current-carrying wire can be measured, and it is equal to a factor involving the magnetic field, B, and it is proportional to the current I and proportional to the length of conductor in the magnetic field L. So the force in newtons is BIL in this case. The unit of B is the unit of force per current times length. You remember that charge times length was moment of charge, or dipole moment of charge, if you remember. So here, current times length is current moment, measured in ampere meters. So the force, the magnetic force B, is the force per ampere meter, which is also called a Tesla. The unit here is called a Tesla. If we consider the force on a bar magnet, on a small bar magnet, placed in front of a larger magnet, or the force on an iron bar of cross-sectional area S in a magnetic field B produced by the magnet, then you can find the lifting force to be F equal to B square S divided by 2 mu naught. Mu naught here is a factor that relates the magnetic force to the medium, which is air or vacuum. Thus, B is related to area, and historically, the magnetic field lines were thought to have a form of flux flowing out of the surface of the magnetic pole and was measured in Webers. A unit of flux is the Weber. So, the magnetic field quantity B, introduced as force per current moment, can also be regarded as a magnetic flux density. Thus, we describe B as the magnetic flux per unit area, or B equal to psi m over A. Psi m is the magnetic flux. If lines of psi m are perpendicular to A, then psi m equals B times A. In general, psi m is BA cosine alpha, where alpha is the angle between the normal to the surface and the magnetic flux. Dimensionally, psi m is force per current moment times area, and this is m times length squared, mass times length squared, divided by second squared times current. This unit is called the Weber. Okay. So B is measured in Weber per square meter, or Tesla, as well as the force per current moment, but the usual unit is the Tesla or Weber per square meter. The force on a current element is in essence a force on a moving charge. Since the charge lies inside the conductor, inside the wire, the force is transmitted to the wire. Another experiment involving magnetic force is that of a moving charged particle, Q, in a uniform field, Bn, produced by a large magnet. This is the case of the charged particle in the cyclotron accelerator. When the velocity of the particle is perpendicular to the magnetic field, the magnetic force on the particle is Fb equal to Qv times B. V is the velocity of the particle, okay. B is the magnetic field, and Q is the charge. Experimentally, the particle moves in a circular path of radius r. The particle is then in equilibrium along the radial line by balancing the magnetic force against the inertial centripetal force. The inertial centripetal force is ma, which is mv squared over r. Okay, and this force is in the direction of plus rho. Okay, so the magnetic force QVB equals this centripetal force, so that the particle is in equilibrium along the circle. So we can calculate the radius of the path, which is mv over qb. The angular speed omega is v over r, which is now equal to qb over m. The period of the motion, which is the time of one revolution, is t equal to 2 pi over omega, which is 2 pi over qb. Compare f b equal to qvb with f equal to ilb. V is dl by dt. So it is q by dt, which is I. So it becomes I times dl times b for a short current element. In vector form, when the current element is not perpendicular to b, the force on the current element is df equal to I dl cross b. If in Ørsted's experiment, the compass needle is replaced by a short current element or a charged particle, since B on the needle is along the direction of phi, dl is along az, so it is equal to dz az, and hence F will be along a rho, since az cross a phi is minus a rho. So a force of attraction, this is a force of attraction if the current element is z-directed, same as in the wire. If we assume the wire along the z-axis to be infinite and the current element to extend along az to infinity, then we can calculate the force per unit length to be F equal to minus I LB, which we stated before, but we still do not have a formula for B. From Ørsted's experiment, B is proportional to I and inversely proportional to distance, rho, so proportional to 1 over rho. So we can write B equal to K I over rho. The constant of proportionality K depends on the system of units being used and also on measurement of force. Experiment has shown that K here equals mu naught over 2 pi, where mu naught is 4 pi times 10 to minus 7, and it has the units of inductance per unit length in henries per meter in SI units. So mu naught has the unit of inductance per unit length, and here B is equal to mu naught I over 2 pi rho in Teslas or Weber per square meter.